Go ahead.
All right, so our speaker today is Bea Adam-Day from University of Leeds. And Bea, you're working with Andrew, right, on your
Hmm.
PhD? Mm-hmm.
Yes.
And she will speak today on the indestructibility or otherwise of subcompactness and Cnsupercompactness. Go ahead, Bea.
Thank you so much. Thank you everyone for inviting me, the whole Cooney group. It's wonderful to be here, total honor. Especially since I will probably be referencing a few of you today, so it's quite nice to be able to talk to you directly. This talk is about, as the title suggests, the indestructibility or otherwise of two types of cardinals. So subcompact cardinals and CN supercompact cardinals. And this is a kind of thing that I've been working on for some time, especially the subcompactness result. Um, and recently I've been looking at Cnsupercompacts as a suggestion from my supervisor, Andrew Brooke Taylor. And it's a kind of an interesting slight disappointment, I would say, but it's still something that I'm interested in, even though the answer is not what I was hoping it would be. So anyway, without without further ado, let's do some maths. So first of all, oh, okay, sorry, my keyboard is moving. So for those of you who aren't familiar, indestructibility is something that you can talk about for a large cardinal. So if you've got an L large cardinal, and this is just sort of general large cardinal, super compact, huge, whatever you'd like, large cardinal kappa, we say that it's indestructible by a class A of forcings if, after you force with any P in A, kappa stays L large in the extension. So the idea is here that the largeness is robust, like it doesn't break down after forcing with whatever class of forcings you're thinking about. In order to do this, you more often than not need to apply some kind of preparatory forcing, and this will just make the indestructibility hold. There are actually instances where this isn't true, where you don't need to apply a preparatory forcing, such as in Andrew's paper on VP. But in general, for large cardinals, you do need to do something to the universe to make it robust, sort of shore it up. So, as far as I'm aware, this first became a subject of interest in 1979 when Lever published his very famous paper where he showed that after forcing with what is now called the Lever preparation, P kappa, a supercompact kappa will be indestructible under less than kappa directed closed forcing. So one thing I'd like to say about this result is that this iteration P kappa, it's an Eastern support iteration of length kappa, as the name hopefully suggests, and it's defined relative to what we now call a Lever function. So this is a partial function from kappa to kappa, which exhibits some kind of anticipatory behavior. Actually, it's often called a Lever diamond because of this, and it's a kind of arguably not the most intuitive function. It's a little bit, it's constructed to be precisely what you need to make the argument work, but its existence, showing that it exists is a little bit of work. But it is, you define it relative to that function. So you have your non-trivial stages of your forcing when your Lever function tells you that you can, basically. So some more indestructibility results. I mean, this is a broad field. There's a lot going on, and there's a lot that has happened that I'm completely ignoring, so I apologize. But this is just a kind of a little idea of what's been happening. So in '89, there was a result by Gittik and Shalah who said that you can make the strong compactness of kappa indestructible under kappa plus weakly closed forcing, which satisfies the Prickwe condition. So this is a slightly more restrictive collection of forcings than, say, what Lever showed, which is just less than kappa directed closed forcing. But it's still, it's about strong compactness, so it's quite a different category.
Excuse me, but the Gittik-Shelach result, it's about strongness, not strong compactness.
That's a very, thank you. Yes, thank you very much. Yes, I've been conflating my sources. Thank you. I don't know who
And
said that.
also,
But
one other thing is that the Lever paper was published in '78 in the Israel Journal, not '79.
Okay, thank you. Dates are not my forte, but thank you for that, 78. So this is, again, sorry, strongness. There are results in the next paper about strong compactness, which is why I have gotten confused. this is the next thing I want to talk about. Obviously, I am missing out a whole load. But then in 2000, I believe, again, I could be wrong, Hopkins published the lottery preparation. So in this, he showed a load of results, including about strong compactness, and he reproved Lever's original result. But what I'd like to show you here is this result, which is a level by level indestructibility result for partial supercompactness. So it says that if you've got some amount of GCH, then using what he calls the lottery preparation, you can make the lambda supercompactness of kappa indestructible by less than kappa directed closed forcing of size at most lambda. So this is relevant to the particular work I'm looking at today, because the cardinals that I'm looking at, subcompact cardinals, are very similar to partial supercompactness. They're not exactly the same, but there's some kind of interweaving behavior between these cardinals. And so the knowledge that this result exists is sort of reassuring to me, and suggests that, for subcompacts, a similar result should be possible. One thing to say here is I mentioned the Lever function for Lever's theorem. And in Hopkins's paper, he uses what he calls a Menas function. So a Menas function for the supercompactness of kappa. And it's kind of I don't want to put a sort of value judgment, but it's a kind of refinement of the Lever function, which kind of tells you that it's not the anticipatory behavior of the function that's important, but it's that you allow for arbitrarily long lengths of trivial forcing in your preparation. So the idea is you do a lottery sum of forcing. I'll say what that is in the next slide. And then you do loads and loads of trivial forcing, and then you do another lottery sum, and then loads of trivial forcing. And this sort of lets your lifting work, and you get the nice closure properties that you require. So the lottery preparation utilizes lottery sums. So I should say what a lottery sum is. So the lottery sum of a class A of forcings is the disjoint sum. So you take the pairs Q and P, where Q is a forcing in A and P is a condition in Q, and then you throw a big 1 on above everything else. And the order is given by this. So if you've got a pair QP, then it's less than or equal to a pair QR. Sorry, I can't read today. RQ, when they have the same first condition, so the Q is equal to the R, and P is less than or equal to Q with respect to the forcing Q. So this has been called a few things. I just really like this terminology for it. It's also been called disjoint sum forcing, forcing side by side, deciding which poset to force with generically. There's a whole load of different names for it, so you may have encountered this under a different name. And the idea behind this particular name, due to Hopkins, is that compatible conditions have all got the same Q, right? They've got the same first element. And so the forcing sort of holds a lottery among all the forcings in A, and then your generic will choose what the winning poset is, and then it forces with it. So big fan of the name, big fan. Now, this is a kind of place where we depart from Hopkins's lottery preparation a little bit. There are obviously similarities in what I'm going to be doing with Joel's presentation. However, what I'll be doing instead of using a lottery preparation defined relative to a Menas function is, for my subcompactness proof, I will be talking about lottery sums of minimal counterexamples. So the history behind this is an interesting one, and I'm not going to give you the full history, but as far as I'm aware, I believe Arthur Apter came up with the idea of to remove Lever functions from supercompactness proofs to use minimal counterexamples where we take the minimality with respect to rank. So this is a kind of idea that was useful in a whole load of proofs. There's some papers from, I believe, 2003 and 2005. And then Philipp Schlicht and Philipp Lücker worked on, instead of using minimal counterexamples with respect to rank, they were interested in minimal counterexamples with respect to hereditary cardinality. So they worked on this with one of Philipp Schlicht's PhD students, and re-showed Lever's proof using this method instead of some kind of lottery preparation or Lever preparation, what have you. So let me tell you what these things are. I mean, the name hopefully is evocative of what it is. A counterexample to the L largeness of kappa is a triple Q lambda kappa. And we have that Q is less than kappa directed closed. Kappa is lambda L large for any large cardinal property, but Q forces that kappa isn't lambda L large. So the idea is Q breaks the lambda largeness with respect to whatever large cardinal you have of kappa. And then we say that this counterexample is minimal if lambda eta is lexicographically least among counterexamples, where eta is the cardinality of the transitive closure. So the idea with the minimal counterexample is you're breaking the least amount of largeness that you can, and you're doing so with the smallest forcing you can with respect to transitive closure.
Could I just ask a quick question?
Sure.
I mean, if you force with a forcing and you have another structure that's isomorphic to it, like another forcing that's isomorphic to it, then it doesn't matter which one you force, it produces the same extensions, right? So why not just talk about the minimal, I guess, minimal cardinality, right? Because like if you have a forcing, you can just pass to one that lives on the cardinality of that forcing and it is isomorphic to it, right? So then you don't have to talk about the cardinality of the transitive closure.
Yeah, sure. I mean, in general, yes. For our specific case, we're interested in the transitive closure because we're dealing with forcings which are in H alpha, what have you. So we're interested in maintaining forcings which have got a transitive closure of a particular size. So you could do this with cardinality, I'm sure, and it would work for a lot of things, but for subcompactness, I believe, I mean, maybe I can work around it, but for what I've been using, I've been worried about the transitive closure a lot. Did that answer your question? You don't look certain.
I don't know. I mean, it seems to me like if all you're aiming for is killing off counterexamples, then you might as well always choose forcings that live on an ordinal or actually on a cardinal. But we'll see, maybe. Right?
Yeah, maybe. I mean, you're probably. I mean, you may be right that it's slightly unnecessary, but for sort of ease of parsing some of the later results, I've opted for this transitive closure.
Okay.
We'll see. We'll see later. Maybe that's not useful. Thank you. So this kind of definition of a counterexample, it works for large cardinal properties L, where if kappa is lambda L large, then it's gamma L large for gamma less than lambda. So such cardinals are supercompact cardinals, subcompact cardinals, Cnsupercompacts, like a whole load. Okay, so now I want to talk to you about subcompact cardinals and define them and talk about some of their properties. So before I talk about subcompact cardinals, I will talk about their close relative supercompact cardinals. And I'm sure many of you are very familiar with this characterization due to Magador of a supercompact cardinal. So it says that kappa is lambda supercompact if and only if there are ordinals kappa bar less than lambda bar less than kappa, and an elementary embedding J from V lambda bar to V lambda, which has critical point kappa bar, and the image of kappa bar is equal to kappa. So this is kind of presenting the large cardinal as not the critical point of the elementary embedding, but as the image of the critical point. And so this is kind of, slightly different to how we would normally present. I mean, normally, one might normally present supercompactness. And it turns out to be very similar to how we or these large cardinals have been defined. So a subcompact cardinal, the definition looks similar, and there's a reason for that. So kappa is alpha subcompact for some alpha greater than kappa if for all subsets A of H theta, no, H alpha, there exists a kappa bar less than alpha bar less than kappa, and then there's some subset A bar of H alpha bar and an elementary embedding pi going from H alpha bar to H alpha and takes A bar to A. And it has critical point kappa bar, and the embedding takes kappa bar to kappa. So the similarities between this presentation and the Magador characterization are abundant. What have we changed? Well, we've added this predicate of the subset A. And so we say, you need to have an elementary embedding for each of these subsets of H alpha, but that's no matter. And we've gone from talking about V's to talking about H's. But really, that is all that we've changed here. So the diagram that I have in my mind is this. And this is what I
Can
always.
interrupt you
Oh,
for a
hi.
second? Okay, so can you go back to the previous slide for a second?
Mm-hmm.
So you can formulate Mogador's characterization in terms of the H alphas also. So really the only difference is that you're adding the predicate.
Sure.
Okay.
I can believe that. Yeah.
Okay.
Yeah. It's this. The predicate is. Yeah, but it's just a little bit of a bit of a pain
And the
actually.
predicate is essentially taken care of by having one more level of supercompactness, right? So if I have one more level of supercompactness, I get the predicate free, right?
Sure.
So
Yeah.
it sort of stratifies in between the levels of supercompactness.
Precisely, yeah, and this is
Okay.
why these were defined this way. So, actually, a history of subcompact cardinals. Their original formulation was due to Jensen, and they were what we would now call, or I would now call at least, kappa plus subcompact cardinals. And then their definition was sort of generalized and stratified by Andrew Brooke Taylor and Cy Friedman, and so they added this alpha to sort of generalize it further. And they also showed that if you've got, let me think of the precise bounds. If you've got 2 to the theta less than kappa supercompactness, you've got theta subcompact. No, sorry, I've got that the wrong way around. If you've got 2 to the theta less than kappa subcompactness, then you will have theta supercompactness. And if you've got 2 to the alpha plus supercompactness, then you'll have alpha subcompactness. So exactly what you said, Vika. If you've got one extra bit of supercompactness, then you get all the subcompactness.
Okay,
And so,
perfect. Thanks. That's what I was thinking.
Yeah.
and so could I just ask, so what Jensen defined was what Jensen called subcompact was just talking about basically alpha being kappa plus in this definition? Okay,
Yeah.
right.
And they're kind of arguably one of the most interesting subcompacts that we have, because they need not necessarily be measurable, but they're kind of, I think they're kind of interesting. So they're kind of the weird. If you had to choose the weird ones, it would be the kappa plus ones. I think
There's a close relationship with failure of square there, right?
very much so. Yeah, absolutely.
Mhm.
Yeah, and that's kind of I believe, I mean, I can't say what their intentions were, but I believe that when Andrew and Cy wrote this paper, they were hoping to sort of bring down this bound to a very precise amount, which was subcompactness. So the diagram that I have in mind is this one. I hope you can sort of understand what I'm going for here. So we have the elementary embedding for A. So this A is a subset of H alpha. And then we've got some H alpha bar and then kappa bar less than it. And this kappa bar is mapped up to kappa, and then this A bar is mapped to A. And so this kind of gives you an idea of the elementary embeddings we're dealing with. And then here are 2 little nice things that are useful to know. So if kappa is alpha subcompact for an alpha bigger than kappa, then it's beta subcompact for all beta between kappa and alpha. This kind of makes sense. And if kappa is alpha subcompact for all alpha, then it's actually fully supercompact. So the stratification goes from weak compactness all the way up to full supercompactness if you have subcompactness for all alpha. So I mean, my hope is that you can see that these are interesting cardinals at the very least. So they are worth looking at. So my hope is to come up with an indestructibility result for subcompact cardinals similar to Hopkins and Leva and all the others who came before. And in order to do this, I need to define a preparatory iteration. So we fix a cardinal kappa and an alpha greater than kappa. We define inductively an Eastern support iteration, and then we have this sequence of thetas and etas which goes along. And these thetas and etas will be guiding our iteration and telling us when we can and cannot have non-trivial forcing. So we suppose that everything up to stage delta has been defined already. So P kappa delta has been defined, and then the thetas and the etas up to delta have been defined. Then we say, well, if delta is sufficiently large, if delta is bigger than all the etas and the thetas, then we actually do a lottery sum of minimal counterexamples. So we let the next stage be a P kappa delta name for the lottery sum of forcings Q, and we have to do some restrictions on this to make sure that we have a kind of nice coherence while we, go up. So we require that the transitive closure of Q is not too big, right, less than kappa. And we require that Q theta delta is a minimal counterexample, and that theta is less than or equal to kappa. So the idea is here we're forcing with a lottery sum of forcings which are minimal counterexamples, and the amount of subcompactness we're breaking at that stage is not too much, it's less than kappa or equal to kappa, and the size of the forcing is not too large, it's less than or equal to kappa transitive closure. And then what we do is always say, well, then our guiding function, we need to redefine that. So the delta eta will be the cardinality of the transitive closure of these minimal counterexamples. And then the theta will be equal to the theta, the amount of subcompactness we just broke of delta. And then if this isn't true, so if delta is not greater than all these thetas and etas, then we just do trivial forcing. And we call the next theta and the next eta just 1. So we'll end up with a sequence of lottery sums of minimal counterexamples followed by loads and loads and loads of trivial forcing, and then some more lottery sums of minimal counterexamples, etc. Are there any questions about this iteration? I'm aware that it's a wall of text and there's a lot of sort of super and subscripts. Okay, that's fine. There's actually I apologize for the superscript. It does seem superfluous, but is actually kind of important for some kind of technical issues. Essentially, we want to know that when we restrict a long iteration defined like this, we end up with the right thing. So we have to worry about what cardinal it's defined relative to. But I'm not going to go into that, so I just thought I should mention it. Okay. Some lemmas which are useful for us today. This one here is a sort of just a little gentle, I don't know, nice properties of P kappa kappa. So P kappa kappa isn't massive. Its cardinality is less than or equal to kappa. And without loss of generality, we can assume that it's actually a subset of H kappa. We're taking a direct limit at stage kappa, and all the stages up to stage kappa are not big. So we can assume that we're in H kappa. We also need to use these two well-known results, and we'll be using them liberally. So if you've got a forcing notion P and it doesn't collapse alpha, and then you've got a name X in H alpha, then for all conditions P and P forces that X is in H alpha in the extension. So if you're in H alpha in V, then you're in H alpha in the extension. And this lemma is a kind of slightly more complicated reversal of the previous lemma. So this says that if you've got alpha, which is regular, P is in H alpha is a notion of forcing. Then for all P and P, if P forces that X is in H alpha, then there's a Y, a P name in H alpha, such that P forces that X is equal to Y. So the idea is that given suitable conditions, this regularity, P being in H alpha, you can drop down and still stay in H alpha, is the kind of gesture. Okay, so at this point, I might like to point out that we have this regularity requirement here, and this will turn up in maybe the next slide as somewhat of a question. So this is the result, the fruits. So this theorem is about indestructibility of alpha subcompactness. So much as we had in Lever's case and Hopkins, if we have kappa being alpha subcompact for a regular alpha greater than kappa, then after forcing with P kappa kappa that we defined, the alpha subcompactness will be indestructible by any less than kappa directed closed forcing Q, which is in H alpha. Mouthful. So first of all, I have questions for myself, I suppose, and I guess for you. I wonder if this regularity is necessary. It works if it's regular, and that's totally fine. I would just like to test to see if I can do this with singulars. And really the only reason is because this lemma requires regularity here. There may be a workaround that hasn't occurred to me yet, but at some point I'd like to think about this a bit more. But regardless, we have this for regulars, and there's quite a few of them, so hopefully that's something. So in order to prove this, we'll suppose that it's not true. So if this isn't true, then there is a less than kappa directed closed forcing Q in H alpha, which breaks the alpha subcompactness of kappa even after we forced with p kappa kappa. If there is such a Q, there's a minimal such Q. There's a minimal counterexample. This will be Q theta kappa, and this theta need not necessarily be equal to alpha. We might have broken a little bit less subcompactness. So we say that this theta is less than or equal to alpha. And the way that we're going to prove this is we're going to show that kappa is actually theta subcompact in Vg kappa G. And here G kappa is P kappa kappa generic over V, and little g is Q generic over Vg kappa. So let's just be clear about what we're doing. This is the sort of proof structure. If you had to remember one image, this would be the image. It's not the most beautiful image, but I hope you can see what's happening. So the idea is here we start with a subset A of H theta. We want to show that kappa is theta subcompact in Vg kappa G. So we want to exhibit a theta bar and a kappa bar down here, and then an elementary embedding taking this A bar up to A. So instead of doing that kind of directly and staying in Vg kappa G, we're going to drop down twice and go into V. And when we drop down twice, we use the lemma, the second lemma that I discussed, which says that you can drop down provided you're regular. And then when we drop down, we'll end up in H alpha. And well, kappa is alpha subcompact in V. So there's this B bar and this H alpha bar and an elementary embedding going up. And then we'll take this B bar and lift that up, lift the elementary embedding between B bar and B, and we'll end up with some A bar, which is located in a nice place. It's located in H theta bar, and an elementary embedding will go between H theta bar and H theta and take A bar to A, just as we wanted. So this is the kind of idea. We're not doing it directly, we're sort of hopping down and hopping up. Okay. So to put this into symbols, what we're doing is we're going to show that for all subsets A of H theta in Vg kappa G, there's a theta subcompactness embedding. Right, this looks horrifying, but I hope you can see what I'm saying here. Pi goes from H theta bar in Vg kappa G, and it has predicate A bar and goes up to H theta in Vg kappa G, and then A. It must have critical point kappa bar, and the image of the critical point must be kappa, and obviously it's a subcompactness embedding, so kappa bar is less than theta bar is less than kappa, and A bar is a subset of H theta bar. So let's do this. Let A be kind of an arbitrary subset out here. Now, since alpha is regular and our forcings are not big, right? P kappa kappa followed by Q is in H alpha, so we can use this lemma that says we can drop down and stay in H alpha. So A looks like the interpretation of B for some B, which is a subset of H alpha in V. Now, kappa is alpha subcompact in V. So there's a kappa bar less than alpha bar less than kappa, and then a B bar subset of H alpha bar, and then an alpha subcompactness embedding witnessing this alpha subcompactness for B. So it looks like this. It has critical point kappa bar, and it does all the things that we hope it does. Now we need to lift. So the way that we're going to lift is we're going to apply the lifting criterion. Before we do this, however, to ensure that everything sort of lands where we want it to go, and we stay in H theta bar at the right points, we're going to add in two extra predicates. So we add a predicate, a P kappa kappa named R that Q interprets, and also we throw in theta. So I didn't mention this earlier when we talked about subcompacts, but since you can encode finitely many sets as subsets of H alpha, you can sort of arbitrarily throw in extra predicates as long as there are finitely many of them, because you can just imagine, well, let's say I took the alpha subcompactness embedding for that embedding which encodes all three of these subsets. So we can just throw these in and it does us no harm. Let me just sort of recall to you the lifting criterion. So if you've got M and M transitive models of ZFC without power set, and pi goes from M to N is an elementary embedding, and if you have that P is in M is a forcing and G is generic over P, and we also have that H is pi of P generic over N, then the two things are equivalent. So there's an elementary embedding pi plus, which we call the lifted embedding. So it goes from m extended g to n extended h, and pi plus of g is equal to h, and pi plus restricted to n is equal to n. So it extends pi and also is this nice elementary embedding between the generic extensions. The existence of such an elementary embedding is equivalent to pi of p being in h for all p in g. So the pointwise image of g being in h. So this is kind of telling us what we're going to do. We're going to lift. And the way that we're going to do this is we're going to show the second condition, which looks a lot nicer to show. One thing I would like to sort of highlight for you at the moment is h is pi of p generic over n. So we end up, since we're dealing with a cardinal which is the image of a critical point and not the critical point, we end up sort of lifting seemingly unevenly. We end up lifting on the left-hand side with p kappa bar, so the iteration defined up to kappa bar, and on the right-hand side up to p kappa kappa, all the way up to kappa. But then at the end, we show that actually these sort of even out, and actually because our embeddings are nicely behaved, we've actually done a full lifted embedding from h alpha in vg kappa g to h alpha bar in vg kappa g to h alpha in vg kappa g. There's a lot of terminology there. I think it's best when I write it down. Okay, so we're doing a lift. We need to do two lifts because if you recall, we are now in V and we want to go up to first V extended G kappa and then V G kappa G. So to do our first lift, this one is not too bad. We noticed that pi of P for P in G kappa bar, here G kappa bar is P kappa bar generic, is just the same as P followed by kappa many ones. We've taken a direct limit at stage kappa bar. We're using Eastern support. And so it just looks like this. It's very nice. And so for all P in G kappa bar, we can actually lift because this P followed by hollowed ones will be in G kappa, the generic over P kappa kappa. So by the lifting criterion, we can lift this alpha subcompactness embedding in V to an alpha subcompactness embedding in VG kappa. But again, the kind of thing I was saying about this sort of uneven lifting is here we're lifting from H alpha bar extended G kappa bar to H alpha extended G kappa. But it's, soon we're going to fix that and it's going to be fine. And we've, interpreted things appropriately. I've left out a few dots. I ran out of enthusiasm for putting dots on things because I've got these bars and the dots. So my apologies. If you think there should be dots, there should probably be dots. But I couldn't work out a nice way of having both of them in the same place. So I apologize for that. So we've lifted this embedding once to get this pi plus. By elementarity, and this is why we've included the predicate theta, this B bar is a subset of H theta bar. And similarly, because of elementarity, if we just take Q bar, theta bar, kappa bar, that's also going to be a minimal counterexample. So this Q bar is whatever's mapped to Q, right? Oh, I've gone too far. And it's a minimal counterexample in VG kappa, and it's chosen in a stage kappa bar lottery by some generic, which we're going to call G bar for sort of symmetry reasons, right? We're having all the G stuff on the right hand side and all the barred stuff on the left hand side. So we've lifted once, we need to lift one more time. And to do this, we're going to use Silva's master condition argument. And for this, we just rely on the less than kappa directed closure of Q. So if you look at the definition of the lifting criterion, it turns out that what we need is this less than kappa directed closure of Q, and then the second lift should work out nicely. So we lift again, and now it looks even worse. It gets worse, and then it gets better. So we get pi plus plus, and this goes from H alpha bar extended G kappa bar followed by G bar up to H alpha extended G kappa G. But now let's notice a few things about this embedding. Well, for kind of brevity and things looking nice, let's call A bar this guy here, B bar interpreted, yada yada. And then let's remember that, well, the way we defined B was the thing that A interprets. So this B interpreted G kappa G is equal to A. So actually A++ is an alpha subcompactness embedding for A, which takes A bar to A. So to sort of make that look nicer now, we've got A's and we've got A bars. So this looks very close to what we want. The only issue is we're in H alpha extended G kappa bar G bar, whereas we want to be in H alpha in VG kappa G. But it turns out that these are actually equivalent to one another. So this H alpha bar extended G kappa bar G bar is the same as H alpha bar in VG kappa G. And this is because the forcings don't do anything to H alpha bar. It's relatively tiny, and our forcings kind of don't affect it. They're strategically closed. They're, you know, very well behaved. So we've got this alpha subcompactness embedding, and what we're going to do is we're going to restrict it to get a theta subcompactness embedding. So if you recall, and this, you know, may sound very alien to you at this point, we wanted to show that there was a theta subcompactness embedding, not that there was an alpha subcompactness embedding. It's actually kind of not what we're doing, but by showing that this theta subcompactness embedding exists for all these thetas, we do show it eventually, but we do so by lifting an alpha subcompactness embedding and then restricting it. So we restrict, and by some kind of usual techniques, right? I'm hoping this is not too shocking to anyone. We can see that H theta bar in VG kappa G is actually the same as H theta bar extended G kappa bar G bar. So just as I was saying, these things all kind of work out. So it looks like we're lifting unevenly, but actually we were doing it okay. And similarly, H theta lifts always does what we like. So H theta in VG kappa G is the same as H theta extended G kappa G. So we restrict our alpha subcompactness embedding in VG kappa G, and we get a theta subcompactness embedding, and it does what we like, right? It's got the critical point kappa bar, and it takes the critical point to kappa, and so kappa is theta subcompact in the extension, and so contradiction, and so we have indestructibility. So this is the end of this proof, and I'm very, like, there's a lot of detail that I'm missing. Obviously, I don't want to bore you with the fine minutiae, but I hope that you could see that what I'm doing here is I'm using lottery sums of minimal counterexamples for a large cardinal, which is the image of a critical point of a elementary embedding, and doing so allows us to kind of build this framework. Are there any questions about subcompactness? Because I'm about to just completely forget about them. So now is your last chance. Okay. Let's talk about CN large cardinals.
Bea, sorry, 1 second. Can you talk more about the master condition, maybe?
Yes, sure. So the master condition is guaranteed by the existence of, or by the less than kappa directed closure of Q. So we chose Q to be less than kappa directed closed. And we need that to, it's kind of, how do I express this? We're going from, the master conditions allows us to do our lifting criterion again, because it's beneath all of the images of the generic. Does that make sense?
Okay, so that's why it has to be in. I mean, do you really work with this G, or it's the
yes.
G, the little G that you have is the G that you started with at the beginning?
Yes.
Okay.
Yes. Yeah, so G is, little tiny baby G is Q generic over VG kappa. There's too many G's. I apologize for this. Maybe I should have used H or something.
No, I just did similar arguments, and I somehow remember ending up with a different generic on that side. So I have to think, but you have a slightly different lifting.
Yeah, it's kind of, the wrong way around almost. You sort of.
Vika, is it maybe, do you mean like you, I mean, it looks like you could fix some condition that would force this counterexample to exist?
That's how I would tend to do it. I mean, I somehow never ended up using the same G because there was that issue. I mean, how do you know you do have a generic extending the master condition, but how do you know it's the generic you started with?
Oh,
Yeah.
yes, this is something that I have neglected to mention. I think actually you're completely right.
Yeah.
If I'm recalling correctly, we do have to do some worrying about what the generic ends up being. So I don't actually think this little g is the same as we started with. I think I was
Yeah, I
erroneous
think
in saying
do
that.
some little bit of like it's a detail, but I could never figure out. There was always that annoying thing.
Yeah, I'm forgetting the precise details of it, but I'm very happy to send you my stuff. Once I've had a look at it, hopefully I'll remember what happened. But there's something in there, and there's a little argument that had to be made, but I can't remember the
Mhm.
precise details. I apologize. It
Yeah,
tends to
yeah,
be one
I
of
would
those things.
love to see it actually. So
Yeah,
I mean, it's
sure.
a
No,
really
I'll send it to you. That's fine. Yeah, because there's a lot of little details which no one wants to see really, but they do end up kind of having an impact. In the specific context of these subcompact cardinals mean that things that you couldn't do for let's say Cnsupercompacts, you can do for here, and vice versa. Things that should work or have historically worked don't end up working. So yeah, I'll send you the full argument, and hopefully that'll help.
Thanks, Bea.
My pleasure. Okay, Cn supercompacts. So, at some point I finished writing up my subcompactness proof, and I said, Andrew, what do I do? And he was looking at Cn supercompacts and wanted a kind of indestructibility result for them. And at first glance, I thought, hey, these Cn supercompacts, which I'll define in a moment, look really similar to supercompact cardinals. So, why could you not have some kind of indestructibility hold for them? They look very similar. Why do they not behave the same? And I was kind of laboring under this idea that they would work and it would all work out nicely, and I could just apply a kind of either lottery preparation, but just be quite clever about it, or some kind of other form of indestructibility. But I've actually since realized that this is not going to work. So before I tell you about that, let me tell you what Cn supercompacts are if you're not familiar. So this definition was devised or discovered, whatever your philosophy is, by Joan Bagaria in 2011, I believe. So Cn, for a natural n, is the club class of ordinals alpha, which are sigma n correct. So V alpha is a sigma n elementary substructure of V, and we write it as V alpha twiddle n V. Okay, so I think these have appeared in the literature prior to Bagaria's naming of them, but this is how we call them. And then a cardinal kappa is Cn supercompact, again for n in omega, if for every theta greater than or equal to kappa, there's an elementary embedding J, which goes from V to M, and M is transitive, has a critical point kappa, and J of kappa is bigger than theta, M is closed under theta sequences. So this is just supercompactness, right? This is theta supercompactness. But we add this one last condition, which says that J of kappa is in Cn. So the image of kappa is sigma n correct, and this is the one extra requirement that you have for Cn supercompacts, which makes them stronger. So there's a lot of work on this, and I won't be telling you all of the work on Cn supercompacts, Cn large cardinals in general, but there's some really interesting papers available looking at a lot of things on Cn extendables, which have got some nice properties to them. But principally among the results that I was able to find is this theorem. So this is from Bagaria, Hopkins, Sopronis, and Suba's paper from, I don't know, maybe 2015. I might be wrong. And this says that, well, it doesn't say this precisely, but it says a more general result, but an immediate corollary of their theorem is that Cn cardinals are never Lever indestructible for n greater than 2. And in fact, they're super destructible. And what this means for a Cn cardinal is that they're no longer sigma n extendable. Sorry, this shouldn't be sigma n extendable. This should be no longer in Cn after forcing with any non-trivial less than kappa strategically closed forcing. So if you take a Cn large cardinal for n greater than 2, you force with any less than kappa strategically closed forcing that's non-trivial, they're no longer Cn. they actually prove a stronger result, which is about sigma n extendables, which is why my typo is there. But this kind of has implications for a large number of large cardinals. And in particular, and I would like to know, maybe this is something that has been talked about before, but I have been unable to find it written down. So I'm very interested to know what people have to say about this. But to see that Cn supercompact cardinals are never going to be indestructible and will be superdestructible for n greater than 2, one needs to only notice that Cn supercompacts are necessarily in Cn. So the elementary embedding that you have, which witnesses Cn supercompactness, will also give you a witness to being in Cn. And so for n greater than 2, Cn supercompacts can't be indestructible and will be superdestructible. So forcing with any non-trivial less than kappa strategically closed forcing will break Cn supercompactness of a Cn for n greater than 2 supercompact. So this is the position I'm in at the moment. This, was not something that I had hoped would happen, but it turns out, that for most of these large kernels, it's just not possible and they're super destructible. I do have questions about class forcing. So, the reason, one of the primary reason why this doesn't work is because you're dealing with set forcing and they're just too correct for indestructibility to hold these large cardinals. So my question, I suppose I've been looking at, but I'm relatively new to class forcing, is what happens with class forcing indestructibility? Can you show anything to that effect? Maybe some kind of parallel of the lever, maybe lottery preparation would do something. I don't know. I don't even know what that would look like, but we shall see. And then another question I have is this bound? Is this it, right? Is this the only thing we can say, or can we talk about C2 supercompacts being indestructible by class forcing, set forcing, sorry. So is this bound sort of negative above 2 but positive below 2? I would love to know. I have a kind of intuition that maybe this is precisely the bound that you need, and anything that's less correct than C2 might work. But I don't have any. I don't have anything that is clear, so I don't want to, over egg this. But it would be nice to know if that was true. So with that kind of open-ended answer, I think I will finish my talk. Thank you all so much for your attention.
Thanks very much, Bea. That was super interesting.
Thanks, Bea. That was so great. Thank you.
Thank you.
I remember that John had a paper with somebody about class forcing over Cn extendable cardinals.
I could believe that he had a paper with
I have to look
Veda,
and it was a positive result. I don't remember what one it was.
Yes, there are a few papers by, I believe it's Bagaria, Magidor, and Poveda. I
think you're right.
Yeah.
That's the one.
But they're two papers that I haven't. So I've looked at their first paper in some detail, but not their second. And I think that's the one maybe that you were mentioning with the class forcing. But something to look at for sure.
Yeah, and I think it's a positive result. I think you can make them indestructible by some nice class of class length iterations. But I don't remember exactly what the reason.
Sure. Yeah, no, it's definitely the next step in my sort of journey, I suppose.
I mean, something natural to look at would be if it's resurrectable, right? Often there are these accompanying results like that, these destructibility results. I could imagine that you could do another forcing. I mean, I don't know exactly how this argument goes, but it seems to me like, okay, so this forcing that destroys the Cn-ness of this kappa, so that adds some witness that is visible in V but not in V kappa, right? That something like that must happen. So then maybe you can force further to add a witness to V kappa to that same thing and resurrect the Cn-ness somehow with some small forcing afterwards, or I don't know, but it would be a natural question.
That's a really good suggestion, and it's not actually something I had considered. I mean, I've heard of resurrection before, but I've not looked at it. So definitely there's so many things, you know, to do. My to-do
Yeah.
list is quite long. Thank you for that suggestion.
Any other questions?
Doesn't seem
Last
so.
chance. Hmm?
I think everybody seems satisfied. Thanks a lot for the talk.
Much for having me.
That was great, Bea. Thanks.